Okay, welcome to the 7th class meeting of EC 202, the Introduction to Probability and Random Processes. In the 6th class meeting, we studied the induced probability space for real random variables. The amazing result was like this. There are many random experiments whose outcomes are subsets of real numbers. So for example, we may assign 0 and 1 to the coin tails and heads. In the case, tossing a coin, that random experiment generates a real number from the set 0, 1. If we roll a die, then obviously the outcome is from the set 1 through 6. So there are many random experiments whose outcome is a real number. But most of the random experiments have different sample space and sigma algebra and probability measures. So suppose you have such two random experiments differently modeled. The greatness of induced probability space idea is that we can unify this part. So we no longer need to specify the sample space of the individual real number generating random experiments, but just use the real number set as the sample space and the Borel sigma field or sigma algebra as the sigma algebra. And the difference is this one. So from this probability space, we may assume that there is an underlying probability space and a measurable function that induces this new probability space. And again, we have another induced probability space this way. So we have successfully unified every random experiment generating a real number. So only difference is this function. And this function is called the induced probability measure. And it's again a set function. So here, p sub x is also a set function, but the difference is that what? What is the domain of the probability measure? This is the Borel sigma field, and it assigns what? Probability. So 0 to 1. Got it? So every subset of this Borel sigma field, this induced probability measure assigns a number between 0 and 1. And this mapping rule differs depending on your probability measure. Got it? So this is the idea. By the way, an element of this Borel sigma field is called a Borel set. Got it? So member of Borel sigma field is called Borel set. So suppose you have this Borel set, the half interval, then you may assign some probability to this event, okay? Or you may say that using this probability measure, let's say P1, so this notation is perfectly same, got it? So probability of event that X is a member of this interval can be rewritten using the induced probability measure and the corresponding Borel set. Got it? So this is the key. And the next great thing is this one. The Borel sigma field for the R to the 1 in this case can be generated by half intervals from negative infinity to some real number x. So only these intervals, using only these intervals, all the Borel sets in a Borel sigma algebra can be generated or built up using countable set operations like complementation, intersection, and union. And you define a new function, now a function only of x, this way. And this is called the cumulative distribution function, CDF, of random variable x. And interestingly, apparently, it appears that this function is a kind of special case of the induced probability measure only for these half intervals. But as I told you, since Borel sigma algebra can be generated by this type of half intervals, actually, these two functions are equivalent. That's why we love the CDF. Got it? So please remember this one. CDF fully describes a random variable. And our engineering or mathematical terminology or jargon is that we say the CDF of a random variable characterizes the random variable. Got it? It means what? First, we may have underlying probability space and a measurable function to fully describe a random variable. Second one is the induced probability measure and this induced probability space. The third one is what? The CDF. So which one do you love? This one. Okay. This is very simple. However, in many cases, you still need this definition. Why? Because whenever we want to define a new concept, like random graph, if you want, or random field, or random polynomial, how can you define? You always go back to this first way to characterize a random something. Got it? So remember this one. And actually, you already know the third one. And the second one is mostly hidden in the high school or undergraduate level textbooks. Got it? Anyway, so the second part of last class meeting was this visualization methods. So just quickly see the graphs. The first one is what? This is called scatter plot, one-dimensional scatter plot or strip plot. And this is from the college entrance exam, at that time called 학력고사. And the second one was the dot plot. And this is very, very famous, the United States FOMC dot plot. FOMC 점도표. And you may use histogram by properly defining your bins. And what you need to remember is that the international convention is what? You use this way to define a bin. Left inclusive, right exclusive. However, the rightmost one has exception. It includes the right end too. And something weird in the histogram, the international standard is that if your sample goes out of this last bin, so you have some sample greater than B sub n, that is dropped. So it's strange. As an engineer, I really hate that idea. Also, if you have the first bin, then if some number, your sample is smaller than A1, that is also dropped. So be careful. By the way, the next homework is due on next Wednesday. Will include a MATLAB programming problem, just one. It has 3 sub-problems that they are all connected, and you use MATLAB histogram, and you need to see this phenomenon. And another thing is that the histogram can be normalized in the sense that the area, sum of the area becomes 1. In that case, you can reduce the size of the maximum bin size to 0. And then we have something very interesting. So the kind of limit of the normalized histogram really appeals to our sense and matches to our notion of the probability density function. And since CDF is defined as this one, you can easily see that your density integrated up to, actually I have to write this way, x plus, right, inclusive, then you have the CDF back. So in this way, PDF and CDF are related. By the way, this is Greek letter Xi, but I'm not a good calligrapher, so this is, how do you say it? Something like this. I don't know. Anyway, so you will enjoy the problem. I made a problem that asks you to consider generate this kind of limit of the histogram by having a very, very small size of the bin. By the way, the normalized histogram idea looks fair when you have a discrete random variable. However, it is not actually. By using the idea of a direct delta function, we can allow infinitely high rectangle with infinitely small width. Then what? We have nice PDF that has direct delta functions. So here goes the example. You remember this, right? So I made up this problem for the master's program entrance exam long ago. And I asked the students like this. Suppose you have a normal number generator. So it generates standard normal, which means zero mean, unit variance, normal random variable. And then its output is processed by a function g. And this function has the input-output relation. This is Chinese character, 입력, 출력. Input-output relation like this. So it takes the sign of the random variable. Actually, I haven't specified precisely, but MATLAB has sign function defined this way. If input is 0, it's 0. If it is positive, it's 1. If input is negative, it's negative 1. Really, it returns the sign. Anyway, in that case, what would be the probability density function of the output random variable? And many students, even though they took the introductory probability and random processes, most of them just forgot and gave me a very shocking results like this. So some claimed that the output distribution, output PDF looks like this because this is the input, this is the mapping rule, output should be this. And it does not make sense, right? Why do you clearly see this is not true? Because as I told you, if you use this idea of using scatter plot and normalize histogram and its limit, definitely output is always either 1 or 0. Sorry, 1 or negative 1. And if you generate many outcomes independently, and if you reduce the bin size smaller, then what will happen? Around half of the outcomes will be located at negative 1. Around half of the rest will locate positive 1. So you have the probability density sum of half delta y plus 1 and half delta y minus 1. Got it? So you have two delta functions in your PDF of y. Got it? Anyway, this idea can be easily generalized, and this is the shocking problem to me when I was a 재수생, retaker of the entrance exam. And my friend, who was very, very smart, so I could not understand why he failed in the first exam. Anyway, he immediately extended the idea of 1D scatter plot to the two-dimensional and solved the problem. He was the only one out of 100 students in my class. And we see the properties of CDF. And CDF is very interesting in the sense that if you take the limit, see that? If you take the limit, x tends to negative infinity, then every CDF must converge to 0. If we do not allow point mass at negative infinity, and if you let x tends to infinity, then CDF converges to 1 if we do not allow a point mass at plus infinity. And since CDF is a probability function, it must be bounded by 0 and 1. And by definition of the CDF, if x2 is strictly greater than x1, then CDF is greater than or equal to the CDF evaluated at x1. Got it? So be careful here. You may have equality here. Got it? And also using the CDF, you can simply obtain the any intervals probability. Sometimes you need to have right limit or left limit to precisely obtain the probability of an interval event. Got it? And also, you learned in your high school math, I still remember, we learned like 이산 확률 변수 and 연속 확률 변수, blah, blah, blah. But that is not defined from the shape of the PDF. It's defined from the shape of CDF. So if the CDF is continuous function for all x, then a random variable is a continuous random variable. And if CDF is a kind of this type of step function, stairway function, which means piecewise constant with countably infinite jump discontinuities. Of course, this is inclusive, exclusive, inclusive, exclusive, this way. Because CDF must be right continuous by our definition. Then this is a discrete random variable. And sometimes we have a CDF that is a kind of weighted sum of this type of function and a continuous function. In that case, we call the random variable a mixed random variable. By the way, there is another class of random variables called the singular random variable, but that is almost not considered in engineering problems. So just remember, there are 4 types of random variables, but one is just not that important for us. Got it? And then we moved to PDF. And this PDF is what? Even though it's formally defined as the differentiation of the CDF, it has very, very appealing intuition. What was that? As we did, you plot a strip plot or dot plot or histogram and let histogram be normalized and let the bin size tend to 0. You generate many samples. Then PDF really, really makes sense in that way. And due to the definition of PDF and CDF, they have this relation. But precisely speaking, we will see later, mathematically, direct delta is not allowed. It's a kind of engineering simplification. Of course, there is a mathematics called generalized function theory. Theory of generalized functions. That includes Dirac delta function, nth order derivative of Dirac delta functions, as you see, signal-gen systems and control theory. But mathematicians, of course, they developed this theory, but they have little bit different point of view. We just say that, okay, here is a rectangle with infinitesimally small with infinitesimally high height. Their area, the product is 1, but they have different approach. And in probability theory, we call, let me show you. This is not that important, but just remember where it is. I put it, yeah. So PDF, this is the precise mathematical description. PDF is the Radon-Nikodym derivative of the induced probability measure with respect to Lebesgue measure. What is that? Just remember this way. Got it? This involves what? Not the CDF, but the induced probability measure. But not many of you will ever see this Radon-Nikodym derivative. Just remember the name, okay? Okay, it seems it's very closely related with the differentiation of the CDF to get the PDF. But it's a more elegant, mathematically correct way to obtain the PDF. Just remember that way. Got it? Anyway, so this is a kind of engineering definition. And be careful. Sometimes we have superscript or sometimes we put plus next to the x. That means you consider right limit of this integral. And existence and uniqueness is painful because you may replace any value on the measure on the set of measure 0. So you may replace for every rational x, if you replace the PDF value to 0, it does not change the CDF. Because if you integrate up to x0, then no problem. Got it? So, of course, that on that rational number, you should not have point mass. If you have a point mass, it's messy, but anyway. So, as an engineer, you may freely use the delta function, Dirac delta, the Dirac delta function, and its integral, the unit step function. They both appear in your signal-gen systems and in your control theory. Got it? So if you integrate Dirac delta function, you have the unit step function. And especially we define in the probability theory, unit step function is right continuous. In some signal-gen systems book, the unit step function is defined strange way, like something like this. In some signal-gen systems book. Got it? And I really hate, but sorry. Exclusive. Let's see. Yeah. So exclusive have something like this. Some textbook in signal-gen systems. In signal-gen systems, whether the unit step function is right continuous or not, it's not that important. But in probability theory, it's very important to use right continuous unit step function. Anyway, so let me skip this. So the PDF of discrete random variables can be written this way, which means you have x-axis and you have Dirac deltas scattered like on x1, x2, x3, x4. And this height of delta functions, which sounds strange, but anyway, if you sum them up, that must be unity. Got it? And if you integrate this one to obtain the CDF, what do you have? You have your step function weighted and monotonically increasing like this. Okay. So your CDF becomes sigma. The index I is the index set capital I, P sub capital X, Xi, and here U of X minus Xi. So only the difference is that the delta function after integration is replaced by unit step function. As you just sense using the limit of the histogram idea, the PDF is always non-negative, right? Histogram can never become negative, right? So PDF is also non-negative for all x. And if you integrate it, it must be 1 because it's from normalized histogram. And as I told you, the PDF and CDF are related this way, and you can compute the interval that way. And also, you may have a lot of tricks like this. So what is the probability of event that X is between A and B, both ends inclusive? How can you obtain it? And you also need limit something. So do it yourself, okay? So we have, for example, a PDF this way, CDF that way. PDF, got it? So you integrate up to X value, that corresponds to the CDF, got it? And this is all about normalization of the histogram, so you read it. And I already told you that this strange, mathematically little bit non-rigorous definition can be made rigorous by using the Radon-Nikodym derivative. By the way, the paragraph also explains the consistency of our use of right continuous unit step function and the universal convention of defining a bin in histogram. So if you have interest, just read it. Ready? Now, here comes the most important example of a random variable called normal random variable or Gaussian random variable. Some people love normal random variable, the name, or some people love Gaussian random variable. And the standard notation is this one. So we use capital N. That means normal. Got it? So this N corresponds to that N. And its probability density function is well known and has only 2 parameters. What is that? Mu and sigma square. And mu appears here and sigma square appears there. What does this mean? When I first saw it, when I was a high school student, it was a pain. So let's start from this simple function. Very, very simple. So what is the shape of e to the negative x squared? What is that? It's symmetrical. And if x leaves from the origin, what happens? Since negative x squared is what? This way, e to the negative x squared should be decreasing very fast and decreasing very fast and symmetrical. And actually, this shape is called the bell curve. Okay. By the way, you may say that it is a bell-shaped curve. However, when people say you have the bell curve, which means that you have e to the negative x squared type curve. Got it? So it's kind of confusing. But anyway, and the shape is exactly something like this. Now, what is the integral of this function from negative infinity to positive infinity? And that is an amazing problem because no high school student or almost no high school student can solve it. Using just one-dimensional integral, you cannot obtain this value. So what's the trick? You remember? Probably your calculus textbook had it. How did you obtain the integral of this function? Anybody? You remember that, right? So instead of obtaining this one, you square it. So you take the square of it, and then what do you have? You have e to the negative x squared dx. And here goes the amazing trick. You use different integration variable, and then somehow you convert this one to a double integration. By the way, why do I have the question mark? Because actually you need a theorem that allows you to combine two multiplication product of two integral into a single two-dimensional integral. And in this case, since you're integrand, by the way, this is called the integrand of this integral. That is called the integrand of the second integration. Since the integrands are non-negative, in that case, so-called Fubini's theorem allows you to convert it this way. And then what do? You transform the integration from Cartesian to polar coordinate. And suddenly you have pi, the number pi pops up. Got it? And then you take the square root and you get the amazing result. So actually, after proper scaling and even shifting, you can find that the integration of this function. Now you have 1 over square root of 2 pi and e to the negative 1/2 x squared equals 1 after you integrate. So let me write this way. So actually what you obtain is this one. This is 1. Now you can shift the function from origin. Then what happens? You can change, 1/2. X to x minus a. And since the graph shifts, the total area doesn't change. So you have still 1, right? And now you already learned in your high school math what happens if your function gives you some integration 1, but if you scale it ax, then what is the value? Yeah, of course, this is really I hate. So what I do is something strange. What I claim is that this is 1, okay? And you may say that, oh, professor, the same thing. You are right. However, this form appears again and again in statistics and probability theory when you so-called standardize your value. Actually, this is a way to, A must be mu in the case. But anyway, that is a way to standardize. So you shift and divide by your actually standard deviation. And whenever actually you have more generally, let me use mu here and sigma here. Got it? So you replace x with x minus mu divided by sigma, and you place a, then you have the same integration. Got it? And what happens if you increase sigma from 1? Your function disperses. Okay. And if you change mu value, then your function shifts right to the right or left. Got it? Anyway, so I prefer rewriting the PDF that way. So do you see the difference? Usually we have this form of PDF defining the Gaussian random variable, but I love this form in the way that this 1 over sigma appears here as 1 over sigma in front, and you have x replaced by x minus mu divided by sigma. By the way, if you convert your data by subtracting the mean and divide it by standard deviation, is called z-score. Yeah. So this is called the z-score of x. Got it? And as you see, the Gaussian random variable has many, many cousins and you may say friends by changing mu and sigma. However, all of them has same ancestor, right? That is what? That is the standard normal or Gaussian distribution. And from standard normal or standard Gaussian, every random variable can be computed when you want to compute the density function or CDF function by the change of variable in this way. And interesting thing is this one. The CDF of the Gaussian random variable with 2 parameter mu and sigma square actually does not have a closed form. By the way, what is a closed form? It's a vague terminology, but usually closed form means that this function can be rewritten using so-called elementary functions. And this elementary functions is also not well defined. Usually, what we say elementary functions even include some transcendental functions like exponential and sine cosine. And you will see that there are some definitions just defining this function itself. They are also transcendental functions, so I really hate. But usually, transcendental functions are kind of have very nice Taylor series expansion, usually. So if we restrict the definition of transcendental functions that way, and if you include all transcendental functions as elementary functions, then this cannot be written in terms of elementary functions. So what do we do? The problem is that the CDF value highly depends on these 2 parameters. So do we need to tabulate 테이블화하다 for every pair of mu and sigma? No. As I told you, we just need to tabulate this function for standard Gaussian. And then using change of variable, we can find the CDF value for any Gaussian with the pair mu sigma square. Got it? So this is now the standard definition, or sometimes capital phi. This is phi. Okay. Means CDF of standard Gaussian and defined that way. And it is tabulated, approximated, upper and lower bounded by many people because it does not allow closed form. Got it? So you remember this figure saying that if you have Gaussian distribution within plus minus 1 sigma, around 68% of the population lives here. And this is why I love using z-score when I give final grade of my courses. What I really do is that I kind of convert your score using this formula, z-score formula. So subtract mean and divide by standard deviation. And if you have around 1.9 or 2 sigma, usually you receive my email saying that, hey, you are genius. Why don't you go to MIT or Stanford, not post-doc, when you go to the graduate school? Okay. Actually, I sent some of your former graduates by sending that emails, a lot encouraging them. Or especially if you take the midterm exam, if you receive my email in the opposite direction, then I will warn you. You got, for example, minus 2 sigma, and I would say that according to my experience of 20 years in postdoc, it's highly unlikely that you avoid getting F. You have two choices. One, drop the course immediately and never see me. Second, do your best anyway, but never forget submitting your voluntary project, at least to get D minus. And actually, around once per 2 years, I had that kind of student who really wanted to take this course as the mandatory for his or her graduation. But he or she cannot find any time to seriously memorize the results. And then I recommended, do your voluntary project excellently. Then at least you can graduate getting D minus, something like that. Anyway, so if you receive an email after the midterm from me, be alert. It would be a phrase or a warning. Okay. Anyway, by the way, the CDF has very interesting feature. It looks like that. So the standard Gaussian CDF is symmetrical with respect to 0, 1/2, right? In some engineering books, they introduce so-called error function and complementary error function that looks very similar to the Gaussian CDF, but starting from 0. Be careful. Ready? Also, from tabulated error function, you can find the CDF of any Gaussian. Okay? So depending on their subject or their major, people love error function, or people love phi function and Q function. By the way, the complementary CDF of standard Gaussian is called Q function. And Q function is, of course, defined this way. See the lower limit and upper limit. It's exactly opposite of the CDF. By the way, the Gaussian PDF is continuous, so including the edge point in either way doesn't change the integral. So we are free to just put x here. And Q function is also very important, especially in digital communications, which I major in. So we communication engineers try to approximate it using elementary functions like this. You see, Q function, even though it cannot be tabulated, is very tightly bounded by an elementary function. 1/2 e to the negative x squared divided by 2. No integral, right? Of course, this only works for x greater than or equal to 0. Sometimes people have found good approximation, but forget about this one. I never have seen somebody using this approximation. But there are some strange approximations like that. And here goes amazing conversion of Q function. See that? Q function by definition is what? An improper integral. What is an improper integral? Either at the end of your integration endpoints, the function blows up, or your integration interval is half interval, like including plus minus infinity, right? And as you see, here you have plus infinity, which means that if you numerically integrate this function, what do you need? You integrate, for example, Q of x0 is this area. You have to integrate from x0 to sufficiently large number, right? But you don't know what is the sufficiently large number. And your tail probability may be very, very important. One good thing for this special form is that, see that Q function? Now you have finite integration interval. Amazing, right? And also, this integral is over some strange variable called theta. And you integrate over this finite interval. For what? This 1 over pi and strange function in the integrand. And your x appears in the exponent of the exponential function, the bell curve. By the way, this kind of conversion of the Q function, which is originally an improper integration to a proper integration, may just be a fun for the mathematicians, but for engineers, especially communication engineers, this was kind of finding a treasure island. So they found a treasure. Using this function, this representation, same thing written in the different form. Actually, this simple formula produced many, many, many PhDs in communications area. Some people exploit this function to find some communication systems performance curve in different ways. Got it? Anyway, converting Q function this way is a good midterm exam problem, but I'm not going to ask because it's no longer a 302 course. So if you have interest, just try it. And you may investigate how can we find this one, for example, in your voluntary project to change your F into D minus, or change your A0 into A plus. Got it? Anyway, this is a very interesting. The last comment about Gaussian or normal distribution is log-log plot. And what is a log-log plot? Usually, we use linear axis when we plot a curve. But in many engineering problems, we need logarithmic scaling of the value and the argument of function. Because sometimes we have some formula appearing in engineering that has something like this form. Suppose y equals 1 over x raised to the power of n, and n is an integer. What will happen in the linear axis? You know the shape, right? Everything looks like that, right? For 1 over x, 1 over x squared, 1 over x cubed. However, what happens? This curve is plotted in log-log axis. Of course, for x positive, what happens? As you learned in high school math, if you take the logarithmic function, log y equals what? Negative n times log x. So this exponent n actually determines whether you will observe this straight line or that straight line or that one. Maybe this has slope -1, -2, -3. Log-log plot is very powerful to immediately see whether your function relation, input and output relation, is what? Is this type of polynomial. And what is the order? Got it? So in many engineering problems, we have the input-output relation approximately 1 over x to the n. Of course, you may have shift or some coefficients, but mostly this way. Then you can immediately identify the relation. Hey, I have a straight line in the log-log plot. Then what do you say? We have a power law governing the phenomenon. So power law means that you have this type of relation between two variables, and you have that type of figure in the log-log plot. Got it? And this is a power law. What about the Gaussian CCDF, Q of x in log-log plot? Do you remember? This is the integration of the Gaussian density, standard Gaussian density from x2 plus infinity. And you see that the integrand function has very, very small value if you have large value of y. And amazing thing is that you still have some curve like this, even though you have logarithmic scales. So Q function is called a waterfall curve because of this shape. It's like 폭포, waterfall, right? Got it? So waterfall curve, if you see a waterfall curve in log-log plot, then what? It's reducing the value much more faster than any polynomial. Got it? See that any finite number will still give you a straight line, whatever slope it is. However, this waterfall curve is very, very fast decaying. Why is it so for the Gaussian? Because if you take a look at the density function, you have e to the negative x squared, which means that it diminishes very, very fast. And we call this area as a tail. This is right tail, the right tail. Is very, very light. Here, light means that if you integrate this value is very small and diminishes very fast. So any light-tailed probability distribution has CCDF that looks similar to a waterfall. Got it? Anyway, so for the other things like mean and variance of Gaussian and moments of Gaussian, we will come back later when we seriously study Gaussian random vectors. Now, we've just seen Gaussian random variables with different parameters, but they have the same form. So let's put them in a set. So this set is the set of all Gaussian probability density functions. Of course, you may define the CDF, the set of CDFs of Gaussian, but let's just use the PDF in this case. And as you see here, mu is any real number, and sigma square is any positive number. So this set includes all Gaussian distributions except the degenerate cases, like sigma is 0, because we cannot divide by 0. So actually, sigma equals 0 cases are all omitted, and they are called degenerate. But anyway, what I want to say is that you may put density functions sharing same shape. Only a few parameters determine their differences. In that case, we call this set as a family. This is the family of non-degenerate Gaussian PDFs. Got it? So we can define a family of probability density functions, especially in this case, non-degenerate Gaussian density functions. Also, we may define different families. Why do we do that? Just let's consider the set of all real random variables. There are too many, right? If I just put a very, very small dot, this is actually this family. Very small, but let's exaggerate. So here goes the Gaussian family. And within this set, different members are distinguished by different pair of mu and sigma square. There are actually other families, very famous and important. And you may say that, wait a minute, we may have very, very strange shape for a PDF, but only a few parameters to define a PDF? Well, that sounds strange. You are right. Okay. So in general, this type of family is very, very special. Only a few parameters, sometimes single parameter. Single parameter is assigned. Why do we do that? That's related with our mathematical modeling. Sometimes we find every reason to approximate our random something as a Gaussian random variable. Sometimes. Then what do you want to do? You just need to find the mean and variance of this distribution, right? And you find your result closely matches to the mathematical prediction based on that approximation. Woohoo, right? And you graduate, getting PhD. And 2 years later, your lab junior finds that something's wrong. There are some different distribution cases. That's good for his or her topic for a PhD, right? And saying that actually we need a Gaussian mixture, blah, blah. Why we stick to this kind of parameterized family, as I told you? Because we cannot handle arbitrarily shaped PDF. And we may find good reasons why we use this family of distribution functions. Got it? Anyway, so you need to get familiarized with these 6 notations. Let's take a look at it carefully. So let's see this one first. It's a set of probability density functions, all named just X. But here, this is theta vector. I love underline, okay? To specify whether it's a vector or scalar. Because we may have more than one parameter, right? In that case, this theta vector may have what? So in Gaussian case, this theta consists of mu and sigma squared, right? Got it? And theta is some index set. In our Gaussian case, what? Theta 1, which is mu. So theta 1 equals mu, and that is this set R. And sigma square is, sorry, theta 2 is sigma square, and it's R. Let me use this way, okay? This R sub plus plus means strictly positive real numbers sometimes, okay? Anyway, so you may confront this type of abstractization, 추상화, in many, many, many problems in engineering, especially machine learning that actually performs statistical inference, classification regression, and other artificial intelligence, anything. Got it? So you must be familiarize yourself with this type of notation that specifies a family of distribution functions. By the way, here we use semicolon. And you may say that, well, let me just use conditioning bar, and I've seen something like this. Actually, these two families are very similar, but actually they are a little bit different. Okay. When you use conditioning bar, what you mean is that this data is a random variable, as you will see in this course, not in this chapter. But when you use semicolon, we haven't yet confirmed whether parameter itself is a good random something, random vector in this case, or not. We don't know yet. Or we have found that theta has no probability distribution. In that case, just hastily use conditioning bar may be very dangerous because you can never find the distribution function of this random vector theta. In that case, you must use this expression using semicolon. Got it? So be careful. Anyway, so this bullet explains why we use parameterized family of distribution functions. That is for probabilistic modeling with only a few parameters, which we may find using statistical inference methods. By the way, this is a good time to talk about the units of random variables and density functions. And you may rarely find this type of discussion in other textbooks. But I've found this is very, very important. In engineering, usually after we observe or measure some numeric quantity, number, we have units like x volts. So actually, x is a real random variable, but we have our units. Sometimes we put the units together. Precise definition of random variable has no unit, right? Because we defined it this way. X is a function from what? The sample space to the real line. And real number does not have a unit. However, in many cases, actually we have units. Got it? So sometimes we have something like this we need. In that case, you should be very, very careful in defining a PDF. And let's see why this is so. And first thing is that whenever you see a transcendental function, 초월 함수, that can be expanded using Taylor series, like e to the negative x equals, positive x. You have n factorial. And what? X raised to the n, right? So you have a power series. 1, x, 2, x squared, 3 factorial x cubed. Suppose x is not just a real number, but a quantity that has units. Then this equality means what? First, this is a number having no unit. And your x now has a unit, like volts. Can you add a number with volts? Now let's go back to our elementary school silly question. Still, I remember those students just for fun saying 1 + 1 = 1. And they say what? Here is a cup of water, and here is another cup of water, and you add them up, pouring, you have 1 cup. What's wrong with it? He or she is precisely correct. You have 1 cup of water, another cup of water, and you have one cup of water. But they have different units. For example, this is what? 200 milliliter cup. This is 400 milliliter cup. So when you consider a unit, then this shouldn't be true. Now let's go back to this problem. 1 has no unit. We know that. Suppose X means some volts. Now you have volts squared, cubed. How can you add up? You can't, right? As you cannot do this. What does that mean? Whenever you have e to the x, x should not have any unit. What does this mean? Suppose you have e to the lambda t, where t is some constant and lambda is a variable. And this is some second. Then you must immediately sense that lambda has unit of per second or second inverse. Otherwise, this does not make sense. And sine and cosine functions too. You know that sine and cosine functions have very nice uniformly convergent Taylor series. And you cannot have any unit for the sine x. X cannot have some unit volt. What if you have sine some a and x has unit of volts? Then this constant must have volts inverse. Sometimes a equals 1, but it has 1 over volts. Otherwise, it does not make sense. Got it? So in this way, you check whether your quantity in engineering problem has a unit or not. This is very important, okay? By the way, when I just became a professor and there was some request that I join the PhD committee. So I sit in the defense and saw some interesting results. And after 2 years, some other people from other organizations published the similar result. So I read it. There was something seriously wrong. Because in their approximation, the exponent had units. Something was seriously wrong. So I just pointed out, hey, some constant is missing. Something like that. Got it? Anyway, let's see these examples. By the way, you can just read these examples yourself. So I will be very, very quick, just pointing out what you need to check yourself. First, we will see some families, very famous families of discrete random variables. First one is Bernoulli distributions. And you know that a Bernoulli distribution has only one parameter, P. And this is the probability of, for example, success in your random experiment. And of course, this is probability. So this parameter has no unit. Probability has no unit. Okay. And you have mean and variance. You remember, right? And you have binomial distribution. That is kind of defined different ways, but you know that it's a summation of independent and identically distributed Bernoulli random variables. And you have now 2 parameters, B and P. That's why Bernoulli B has 2 parameters. You remember this, B and P. Probably you read it this way. And what is the mean? NP. What is the variance? NPQ. What is Q? 1 minus P. That is what you remember, memorize, right? And now Bernoulli distribution has, a binomial distribution has this shape of PDF and CDF. And here goes discrete uniform ranging from 1 to B. So they are integers. So you start from A and ends at B. How many point masses do you have? 큰 수 빼기 작은 수 더하기 1. You remember, right? From your high school. B minus A plus 1. That's why the height, okay. Height is 1 over B minus A plus 1. And let me ask you, A and B can have a unit or not? See that? This is exactly the probability. And you have one that is unitless. What does that mean? The denominator should not have any unit. And it is also added by one. So no unit, right? In this form. Okay? Sometimes this 1 A to B may have some units. In that case, actually, you have some constant that just removes the unit from your quantity. Got it? Anyway, here goes geometric distribution. And geometric distribution is related with binomial distribution. It's like you toss a coin and you assign 0 and 1. What is the number of tosses you first see the heads, something like that. And the distribution has what? The PMF has the term exactly a geometric series, geometric sequence, 기하급수, geometric sequence. Okay, 기하수열, sorry, 기하수열. That's why it is called geometric distribution. And you may find the mean and variance, even though I didn't teach, but you already know. Another important thing is discrete memoryless property of a geometric distribution. This is very clear in this problem. Suppose you toss a coin and you want to see the first heads. And unfortunately, you haven't yet seen up to 99 trial, no heads. Okay, so this event means that x greater than 99 means that up to 99 trials, no heads, right? And what is the probability that x is greater than 109? Something like that. So you observe x, sorry, just a second. X is the number of coin tosses. Sorry about that. So x means that number of coin tosses greater than 99, which means that, as I told you, no heads up to 99. And this means that x is greater than 109. And you can easily, if the coin tosses are independent, say that this is simply same as this one, right? So your condition that I haven't seen up to 99 trials has nothing to do with your future success. This is called memoryless property. By the way, interesting thing is that only geometric family of distribution functions has this property if the random variable is discrete. Then you may wonder, then is there any continuous random variable that has memoryless property? Yes, and that is the exponential family, as we will see. Anyway, here goes another thing very similar to geometric distribution that is called hypergeometric distribution. And this is related to, okay, I cannot turn it off. Okay, I turned it off. Okay. Anyway, and just to read this episode, 홍시 학부모의 분노, I found it from Facebook. The story is like this. So you have your throw draw in your elementary school, and the students are sorted according to the last name. So 가시 student, 가, last name 가 comes first, and Hong probably comes very, very late. And the parent got angry because my kid is treated unfairly, something like that. And this is a famous problem. And using symmetry, usually, you can show that if there are only 10 successful throws, then the probability is same. But you can also use hypergeometric probability mass function to get the same result this way. So you try that. And there is another very important family of distributions called Poisson distribution. And here goes the probability mass function. And you can also find probability cumulative distribution function and others. By the way, sometimes instead of using Poisson lambda, sometimes we love using Poisson lambda t. And as you see here, this lambda is the parameter in the exponent of the exponential function. So now, if t has the unit of second, you immediately sense that lambda has the unit of per second. And that will appear when you study random processes, especially Poisson random processes. Anyway, we are done with up to discrete random variables, and you read it, and I will cover these continuous random variables and move to the next topic. By the way, our quiz on Wednesday will cover up to the Monday contents of the class meeting. Okay, that's all for today.